should I start?
Okay, so maybe I should just say, okay, so this is the first meeting of the spring term. So it's a great pleasure to have Antonio Viruel from University of Malaga. And we are going to hear about path partial groups. So thank you.
Okay, so thank you. So this is my second time in Turkey somehow, but this time it's virtual. Yes, I'm going to talk about these path partial groups, which is a joint work with Antonio Díaz and Rémi Molinier. So I'm now going to adjust this thing. So when I write down, you see me? Okay, so this lecture is about one motto that a popular motto. Can you read this, or probably it's too big? Right, they'll say groups are symmetries. So then the question is this true? Well, that surely depends on what you want to be symmetries, and essentially that means in which category you are. So to make it kind of a question, the problem we are going to deal with today is question, fix a category, C is any group represented as out in C of X for some X, an object in C. Well, if so, C is said to be universal. Right. So, yep, that's the kind of easy questions to understand. So we want to give any group, try to find an object in a category, and then the category is fixed, right? So that's the tricky point. We all know that the groups show up like automorphisms of Kelly graphs, but if you are not working in combinatorics, you want groups to be like people there in built-in acting on spheres or product of spheres. So your object could be a more restrictive category, and then you fix the category C, and you want to find out whether any group can be represented as the full group of automorphisms of an object in there, right? So then identifying universal categories is hard. It's hard, right? Just to get a sample of a glimpse of how hard this is just think of inverse Galois theory. Right. So if you're an algebraist and then you want to think Galois groups are just automorphisms of field extension over the rationals, right? And you want to think of normal separable Galois extensions, and you want to know whether any finite group can be realized as the full group of automorphisms of that extension. So that is inverse Galois, which is kind of open problems. Then we know that graphs, and if you think this inside the category of quivers or direct graphs, are universal. So we don't know this one. Are universal, and then a kind of theoretically, if you want to understand groups and you want to represent the groups as symmetries, you may try to make a kind of loop and want to represent groups as symmetries of groups. So groups is not universal. Indeed, there is no group H such that out of H is isomorphic to any cyclic group of order, even to integers. So you cannot find any group like that, right? This is a kind of interesting exercise. Prove it. This is a seminar, so you can just spend a few seconds trying to think about that. And then the point is that groups are too symmetric. Right, just a hint how to prove that there is no such a group. Well, you know that you get the center of the group H, just get into G, you get a quotient which is inner automorphisms of G, then this gets into out of there were G's and now there was H's. So H, 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 and then this project to outer automorphisms of H, right? And then, well, if H no abelian, then this is non-trivial, right? So whenever you start with something which is not abelian, then you start having too many things here, right? And then if H is abelian, then somehow you get always here an automorphism which squares the identity, right? So whether is either E could be minus identity, taking the opposite element, right? And that will be an automorphism of order 2. But if you start with an elementary abelian, that is not going to be, right? But then with this rank 2 elementary abelian, you have a swap between 2 of the generators, and then you get an element there, right? So there is no way that you can get a group of all order, non-trivial order here, right? That's somehow the trick. And the funny thing is that this thing that groups are too symmetric that you get inner conjugation in here is so important that there is this theorem. I'm not going to pronounce these surnames because I don't want to mess up. And let's say that for every group G, there is this H simple group such that out of G, out of H is isomorphic to G, right? So somehow groups are too symmetric, but there is a quotient of the category of groups that is good enough to be universal, right? So groups is not universal. But a quotient category is, right? The quotient category is just a representation category, right? So then the question we are going to address today is, can we find, we get groups embedded in some category, find C category, such that we get groups fully embedded in C, and C universal. So the question is whether we can just extend somehow the category of group
to get a universal category.
So have I misunderstood? Have I misunderstood this theorem by Grenoble et al? Should that be ought H as I saw,
yeah.
or should it be out?
You are completely right. Thank you. Thank you.
Otherwise, it's inconsistent with what you just said, right?
Yeah. It's a pity.
Also, I want to ask you about. Sorry.
I was making a joke. Yeah, but
the graph one. So by this graphs being universal, or for all this discussion, do you mean like groups are discrete here, or like I don't see why like compactly groups are inside graph automorphisms of graphs?
Because you don't like infinite graphs, right?
I see.
Yeah. Graphs. Yeah. So indeed, this theorem involves things about cardinals, right? When you get infinite groups, right?
Okay. So it is actually true that every group is automorphism.
Yeah.
Of some graph. Okay.
Yeah. So essentially, what you do is just you construct a Cayley graph, and then you make an arrow substitution, right? An arrow replacement. So in Cayley graphs, you get an arrow, and that arrow have a color and an orientation, and then you codify that color and orientation with a subgraph, a rigid subgraph, a graph that have no automorphism. And whether or not there are enough rigid graphs to make that replacement is a kind of a sec-theoretical argument. So for a Lie group, constructing a graph like this would be a huge one.
Okay. Thanks.
Okay. So today in theorem A will be partial groups. Is universal. That is, for every group, G, there exists P, a partial group, such that out of P is isomorphic to G, right? And well, so the groups embeds in partial groups, full and part universal, right? So it's an answer to the question. So that is somehow the kind of more important result, and I will just show variation of the result. So should we recall what is a partial group, or yeah, better? Okay, so I'm not getting into details, right? So partial groups were introduced by Chermak to model the local structure of finite groups. But this is a kind of a very algebraic object and combinatorial, right? So partial groups is just a tuple, and in which, well, it will behave like a group, but also it's a partial group. So that means that the only restriction is that you are not going to be able to multiply any two elements in that group, right? So there is a set M that plays the role of the actual group, and then you get words in that set. So that would be a kind of elements you can multiply, but no, you can just multiply a few of them. How many of them? Well, at least you can multiply the ones you get here. And then if you concatenate two words in here, then you should be able to split these two to get in here. And then there is a product. The product goes from this subset of all the possible words. So you cannot multiply anything. And this product have a kind of a obvious sense, like when you multiply one element and nothing else, you get an identity, which is the first question. The second one is like is associative, right? And well, in particular, if you can split any word, like a concatenation of two words, those two words have to be in there. So in particular, the empty word have to be there. And then concatenating the empty word does nothing. So the empty word is just the units. It's like a combinatorial group theory. And well, like in any group, you should have a kind of inversion. Inversion operates in the obvious way. So wherever you have a sequence of words, of elements you want to multiply in your partial group, then you take inverse, then essentially what you take inverse of all of them and reverse the order. And obviously, when you multiply one element by its inverse, you get the trivial word. So these are the objects. Anything here you want to know more, or? Essentially, you have to think like a partial group is just, you get a multiplication taking inverse, but you can multiply everything, but just a very few combination of words, of elements in M, right? So M is the set of elements, D is the set of words with these elements that can be multiplied. And then, well, to define a category, you need to know the morphisms. So whenever you get two partial groups, partial morphisms is just, well, like in group theory, you get between the two sets, you get a set theoretical map. And then that set theoretical map is compatible with the multiplication. So in particular, if you can multiply things in here, and then you apply the morphisms, then you should be able to multiply in the second one. And then it doesn't matter whether you first apply the map and then you multiply, or first you multiply and then apply the map, right? There is a notion of kernel, and well, and there is a notion of automorphism. So it's a category, right? And then groups, embeds in partial. Full by taking any group G, what you get is just G, take all the monoid of words in G, the standard multiplication, and the standard inverse. Right? Because in a group you can multiply everything, right? That's it. So yeah, just think that the only important thing about partial groups is just multiplication is not well defined in all the elements. So you just get a few elements in which you can just make the multiplication, but there is a multiplication and a taking of inverses. So now, let me give you a constructive and intuitive idea of proof. For theorem 1, or theorem A. Okay, so we know that that graphs inside Quiver, both categories are universal. So the idea is construct is, well, I get here group, then there is G quiver such that out of G is the G star 2. So this is the first point. And then the second point thing from G, I want to construct partial group DG such that out of this partial group I have constructed is isomorphic to the graph I got, right? So the very first step is nothing, is just the fact that the quivers and graphs are just universal. So we are going to concentrate in the second one, right? And then, well, recall a partial group is just a kind of notional group in which you cannot multiply everything, right? And we already have that kind of a structure already in algebra, right? In algebra, you get path algebras, right? In which you get a kind of a algebra structure in which elements are path, and then the key is that multiplication is not always not degenerate, right? So the only thing is that well, when you cannot compose or you cannot concatenate path, what you do is just you define that multiplication to be, or that concatenation to be the 0 element, right? So the idea is here, well, we are going to mimic that construction. And now if two paths cannot be concatenated, we don't worry because we don't have to multiply everything, right? So we are going to make so now let the G with vertexes P, E, a quiver, a vector graph, and now I want to define this partial group. So I have to define this kind of things, the product and the taking inverse, right? So, well, if you want to mimic that thing, essentially we do, these are going to be paths in G. Let's see, D, we don't know what it is so far. P is going to be path concatenation. And well, and then there is an obvious way to define an inverse when you get a path, which is orientation, reversing the orientation. Right. So now let's start making some computations just to make it to be able to define things, right? So the very first thing is just well, since we are going to make path concatenations, right? The first thing is that we don't want to, so we are not going to be able to multiply all paths. So here we are going just to get a sequence of P1, Pn paths such that the end of one path equals the source of the next one, right? So we can concatenate them. And what else? Well, we should be able to reverse all the elements. So in particular, we should be able to reverse paths. So every path should be reversible. So in particular, edges should be reversible, right? So if I get a P, well, it's a quiver, so it will be another part, P1, P2, and edge, then P2, P1 also should be an edge, because this is going to be v1, v2, -1, right? So since every edge can be reversed, so then essentially what it means that we are not dealing with quivers, we are just dealing with graphs, right? Every arrow in my directed graph or quiver can be reversed. So it's going to be a graph, not a quiver, right? So what else? Also, we have got a zero length. Well, also since we got a graph. This sentence have no meaning, right? Because if path is a sequence of edges, and then edges are not oriented, so it's kind of meaningless saying end and source, because there is not an end and a source. So here, then what we have to do is just, instead of saying that we are considering path, what we are just doing is just we are just considering and also path here. So I'm not here they're not path. Now I want to make now I need an orientation in the path. So there are sequences of vertices. So these are just P1, PR, and some product of PI EV and PI plus 1 have to be an edge, right? So now in this way I make an orientation, because I put an order in the edge, in the vertices, and then I say that one vertex to the next one, there is always an edge. So then I codify paths, and when I get in here, well, but then instead of getting these things, what I'm going to get is just sequences of vertices here, right? Concatenations of those things. And everything is like a vertex, right? What else? So essentially, just to get more into the combinatorial feeling of group theory. So this is a sequence, so start looking more like a word in vertices, right? So this thing now becomes words in the vertex X. Okay. But then I go to the zero length path. So these are just sequence of one vertex, right? And then if you get just one possible option, right? So essentially that means that p squared have to be 1. So then here, when you define the set, you don't get the full every word, but then you need to divide by the words in which vertex -1 equal vertex, right? But then so then even here you don't get path concatenation, but word reduction. Okay.
So Antonio, can I ask a question?
Yeah,
so when
sure.
you move from quivers to graphs, you not only got rid of the direction, but you also got rid of possibility of loops and multi-edges. You are now working no loops setup.
As soon as I make this, you get rid of the loops.
And no multi-edges because of your notation.
Yeah, exactly. So then here is just, I'm not getting technical, just kind of constructive. So graphs is going to be simple graphs. So no multi-edges and no loops. So I'm getting here. And then what else? Recall, I want to get very, very close to the group of automorphisms of the graph, right? So we want to get rid of inner conjugation, right? So because in this exact sequence of a group and automorphisms, you want to get rid of inner conjugation, right? So we don't want things like a path v, v1, vn, v minus 1, but this is happen to be v, v1, vn, v, right? So if I can multiply this, then I can multiply this. So this is going to be a path, and I don't want, we don't want this. Forbidden, I don't know how to do that. No. Right? So essentially, when I go up here, it's not that I want a path, but I don't want closed paths, right? So if I come here, what I want is just basically reduce words in the vertex x divided by v equals v minus 1. Right, so cyclically reduced words means that whenever you permute cyclically the words in here, they cannot be reduced. In particular, they don't start and finish in the same element. So in particular, they are not closed loops, right? So these are not paths, sorry, not loops. Right.
So I'm sorry, can I ask a question? Are you going back and are you modifying the original definition, or are we?
We are constructing the definition. We are constructing the definition. So I started with what a partial a path algebra will be. A path algebra will be just take any path and then make a path concatenation. But whenever two paths cannot be concatenated, you make it then 0. Right, the product to be 0, right? So then, since we are dealing with partial groups, we don't bother if something cannot be concatenated. Essentially, we say that those things cannot be multiplied, right? So first, in here, I start with just paths, right? And here we're just a path that I can concatenate them, right? And then I'm going to extract more structure just using the actions of partial groups, right? So in path algebras, we also have a reversing orientation. Well, but it's not always true, right? The reason, well, it's not true, right? In path algebras, you don't get a reversing orientation in paths, right? So in particular, one of the actions here was that you should be able to invert everything in M, right? In particular, you should be able to invert any path. In particular, you should be able to reverse every edge, right? So essentially, then you get that the edges, every edge, anytime you get an arrow from one vertex to the next one, you should get an inverse, another arrow returning to the original vertex, right? So that means that well, your quiver is indeed a graph in which edges are not oriented and they are have to be thought that they have both orientations, right? And when you do that,
but actually, I'm curious about this point, because you like, couldn't you have just imagined that you had two separate edges, you know, with opposite orientations, and that those were actually representing different different words or different elements of your like it seems like you're making a choice to go from quivers to graphs here, which
well, here I'm making no choice at all. I mean, just thinking that I delete quiver, put graph, but then I kept the orientation here.
Oh, okay.
Yeah.
I'm sorry.
So,
it's your definition. I don't mean to. Yeah. I'm just trying to understand what the definition is and what the conclusions are.
Well, you know, edges are not oriented anymore, but then path have to be oriented. So path become ordered sequences, while edges are unordered pairs. So, right? And then since I use zero length paths, like making no moving, I have to add this new relation, right? And then since when I do path concatenation and I have to get into group theory, I also do word reduction. So that's why I get first only this part, reduce words with this extra assumption. And then also, and this is truly a kind of a artificial thing that I make a choice because I don't want to get inner conjugation, right? If I'm mimicking only path algebras, this is not going to be there, right? And here's just the key points that I want to get rid of inner conjugation. So I don't want things like these ones. So essentially what I get is just, I don't want a closed path, right? And when I think paths as sequences of words, closed paths are cyclically reduced words. So path, so finally, right? Given a graph G with the vertices P and edges E, the path partial group associated to G is, well, as no, I still have another thing. Sorry, I still have another thing. Another thing that which is not a choice. Now I assume you get a sequence like V1, Vn, and then this is one of if of our elements or not closed path, and I get another edge like Vn, Vm plus 1, right? So these two sequences kind of can be multiplied. So I then get the multiplication of V1, Vn, Vn, Vm plus 1. And then if you make this, just recall that V and V inverse are the same thing. So when I multiply, I have to make a path concatenation and then word reduction. So this will be V1, Vm minus 1, Vm plus 1, right? So that is kind of strange because to make this a path, you need an edge going from here to here, right? So essentially means that whenever I get a path and another path, I can multiply them. We want this guy to be connected to the elements in here. So this another thing that is different from path algebras is like here. The final statement is that you don't want paths in any place. You want paths in complete subgroups, so in cliques. right? So this is going to be a union of C inside V click of cyclically reduced words in C divided V equals V square, right? So now, so these are not closed paths in a click. Do you know what is a click? It's a subgraph which is a complete one. Every two vertices are connected by an edge, right? So since I have to be able to make this kind of multiplications in here, right? So whenever I multiply something with something like this, there will be cancellations here in the middle, and I want this vertex still to be connected to these ones, right? So I get rid of this problem with asking all the paths that can be multiplied to be in the same click, right? So again here, so these are just paths.
Oh.
See?
Or
yeah.
you could have not allowed them to be multiplied. Yeah, it's a partial group, so it doesn't have to have multiplication.
Yeah. I could do that too. I could do that too.
This is the way it works, I guess.
Essentially, that's the way when you make it the kind of a general construction, you can define it in a non very ad hoc way, right?
Okay.
Right, because just like kind of a spoiler, I'm going to take later on. I'm going to take colimits on clicks in a poset, right? So when I'm get out of the kind of intuitive construction, we are going to get into functorial constructions and categorical ones, and I want to know very well which things I can multiply and which not. So finally, the path partial group is just path of G is going to be like a empty multiplication inversion, where ims are just going to be, as I said, taking C, V clicks. So I'm going to cyclically reduce words in C with the quotient B equals B minus 1. Then D is going to be, again, union of words in M, just I'm going to call that thing MC. And this is going to be a word reduction. And then just inversion of word, right? Because since taking inverse is just letting the vertices as the alphabet like it is, so just taking inverses is just reversing the word order, right? So taking palindromic words. So now finally, so to prove that out of this PG is isomorphic to out of G. Notice that every element generates C mod 2 as a group of P of G, right? Vertices are the only involutions in path of G, right? So I get nothing but these are just the only finite groups, right? finite subgroups. Moreover, two involutions V1, V2 that are in here. So we know that V1, V2 can be identified with vertices in V, can be multiplied if and only if V1, V2 is a path. That is V1, V2 is an edge, right? So then V out of G induces well, an automorphism here is just set maps vertices to vertices and edges to edges, right? So induce a morphism here. Now I will just call it with the same word. That since the partial groups indeed generated by these involutions, by the vertices, so that takes any V2, V, right, and any sequence V1, Vm2, V, V1, V, Vm, right? And since things, if something can be multiplied here, it's because I already have a path here that can be concatenated, and here they can be concatenated too because this induce a map between the edges too, right? And if I get phi, an element which is an automorphism of a path of G, right? Then phi maps involution to involutions. So induces from vertices to vertices and composable elements or elements that you can multiply in PG to composable. And well, we already so edges to composable elements. In PG. So phi induce from edges to edges, right? So in that way, anytime I get an automorphism in the path partial group, then I get an isomorphism in the graph. And whenever I get an isomorphism in the graph, then I get an automorphism in the path partial group, right? So this is kind of the very easy approach, right? And then not so friendly. Well, in case you found this friendly, right? But not so friendly approach. Let's say therapy. So let that graphs be the category. So I'm going to define a category in which objects are just pairs G, H, where G is vertexes, edge set, so this belongs to graphs. And then H is just a collection of groups, one for each vertex, right? And then morphisms. As you can expect, it's just pairs of F I don't know, would be phi CV, V belonging to V1, where psi goes from G1 to G2 in graphs, and then CV goes from HV to HC of V in groups, right? So this is like a decorated graphs. It's like a Serre style. You put a group in each vertex, but you put nothing in the edges, right? Just things on the vertices, right? So then there exists a functor n that goes from decorated graphs to partial, that takes on objects. When I get a GH, it's just MG product of inverse. So n will be, well, is defined in 2 steps. For every click C in V, define MC to be cyclic reduce words in C divided by the V means 1. DC is just words in MC, such that words in MC, such that the reduction of every subgroup subword belongs to MC. This is just well, this is just oops, sorry. This is cyclic word, cyclically reduced words in the free product C belongs to C of the HC. So there's no word reduction here like this, and this is a word reduction. Means 1 is just a word inversion. Okay. So for each click, you define this thing, which happens to be a path partial group, and then the second step is just clicks in G if rise to a poset delta of G, and define M of G to be the colimit of these things, MC. So path partial groups have limits and colimits. So you take the colimit in there. Right? And well, the proof is just essentially the same. Moreover, if PHV V belonging to V are just groups finite, there is an exact sequence that goes from
you take out the H V belongs to V, that gets into out of MG, and then goes to out G. Not short. If HV equals HV prime for all V prime in V, then the sequence above is short and split. So so the group of automorphisms of this MG is going to be out of HV, brave product out of G, right? Just think that every automorphism of the graph is going to be a permutation of the vertices. So think of that as a permutation group, and then you get a brave product in which like of signet permutations, in which in each permutation have a sign which is given by an automorphism of the group HV, right? Yeah, and this is kind of the technical theorem. And essentially, if you want to recover, theorem A is recover theorem A taking HV equals sigma 2 for every from every vertex M G, well, with H, right? Then, and you take automorphisms of the thing to get out of G. So I have 0 minutes, so this is a good point to finish. And if you want an application, then you have to ask in the question period or whatever it's called. So that's it. Thank you.
Thank you, Antonio. Thank you very much. So any questions for Antonio?
I have a question.
Yep.
So these decorated groups with assigning a group to every vertex, is it equivalent to maybe assigning one to the edges and think as graph of groups, or is it slightly different as a concept?
There is no relation, but well, I mean, you can do edges. Okay, you can think of the disjoint groups and think that the edge is a trivial group, and then that will be a graph of groups.
Mm-hmm.
But it's not essentially graph of groups, right? Because you don't get the edges have no group associated to them, no subgroup associated to them. So, but you could probably. Can you do
But
that?
I mean, if you assign one to edges and look at automorphism of the whole thing as a graph of groups, would you get the same automorphism group? Like if as like you considered it as a
okay,
group?
So from group graphs, like you're using like a Lasser, is like a defining poset, decorated poset, right? Because you think of inclusions, right?
Mm.
Okay, so you have one vertex, and then here you think that these are just V1, V2, and here you get H of the edge, right? And then usually when you are thinking like a tree of groups, Lasser, this guy, this is included in here and in here, right?
Mm-hmm.
So somehow you are thinking like
I guess you need, then the automorphisms will be different, right? Because anytime you get a map from here to get a f of hp1, yeah, so
I'm saying all trivial. HE, if you take
yeah,
them all trivial.
If you take the all trivial, it's the same, right?
It should be all true. If you take HE is all trivial, so it should be essentially same automorphism.
No, but then you cannot take all trivial, right? Because here, look, here you're taking clicks and then you're taking free products, right? So if you take the trivial group here, you get here the empty set, right? So these groups cannot be trivial.
But in the graph of groups, you don't take the pre-product with edges. You take pre-product only with vertices, and then identifications comes from edges.
Yeah. So essentially you get this, right?
Mm-hmm.
Right, and then essentially you get finally here the amalgamate product.
Yeah.
So essentially, so I guess there shouldn't be any big difference, but I'm worried about whether there are more morphisms, because you somehow you are not considering morphisms from here to here that have to be compatible with these ones. Right? So since in my case here I'm taking the trivial group, there is no there is no compatibility thing about how it's going on in this map and this map, right? But if you put a group in here, then you have to make a compatible this thing when I take this thing, right, and I write the PHP1 PHP1 PHP2 PHP2 and PHE. There is a kind of compatibility question here, right?
But if you take trivial, essentially, you wouldn't get that.
Yeah, exactly, because here we got the trivial group here always. Yeah. But if you want to make it even more decorated, putting here in there, yeah, then you have to be careful about which are these maps, because you need a commutative diagram.
My second question actually related to this. So suppose that I can think this is graph of groups with edges 1, and then there's two notions. Then the notion you're defining, the partial group, and then there is the group Serres defines associated to a graph of groups. So their automorphisms are different.
Yeah. Because
that will be different.
Yeah. Like if I, if I do our construction, right? Mm-hmm. You get okay. So trivial example. G is just P1, P2, no edges, right? Mm-hmm. Right. So if I take groups, I will get set or sum of 2 if I want the p squared to be trivial, right? But if not, I get the path partial group associated to G is just P1, P2. It's like a P1, P2, PM, PM, right? These are the or even to make it even clearer. if you take the colimit using group theory, like when you do with spaces, you get this one with groups. And if you do word constructions, you get something like this. Or V1, V2, right? Just 2, 1, of course, the cheater, right? So the path partial group associated to the discrete graph with 2 vertices is just 2 vertices in which each vertex can be multiplied with itself, but not between them. And if you do that, the kind of a tree of groups associated to that, you get either if you put no extra action, be SIMO2 or SIMO2, depending.
Yeah, the partial group automorphism group is C2, I guess. Like
here, yeah, exactly. It's just you can just permute these 2 copies, or this is set, right?
Yeah.
And this is set, and then there is this thing, right? And there is a -1 because I'm not adding the extra assumption SIMO2, right? So this one SIMO2 permuting, and here you get infinitely many. Right?
Yeah.
Oh, we get a cut there.
Yeah, that's explained by